So, good morning everyone. Today we'll be talking about finite automata. So, the first major question is what is finite automata? So, the finite automata can be simply defined as the machine that is used to recognize some patterns based on the given inputs and that changes its states automatically accordingly given to the given inputs. So, continuing on, the finite automata is of two types. That is, the first one will be without output, and the second one will be with output. So there are three states in this in the without output part. The first one is DFA, the second one is NFA, and the third one is epsilon NFA. And for the output part, there will be a Boolean machine and Mealy machine. So let's continue on the discussion with the first one, that is DFA. What is DFA? DFA is basically defined as deterministic finite automata. It is a collection of five tuples, same as we described in the finite automata. So what are the five tuples? So the first one can be defined as Q, which is the finite set of states, epsilon, which is the given set of inputs, Q naught, which is the input state, F, which is the final state, and epsilon, which is the transition function, which can be defined as Q cross input that gives the output as Q. For example, now let's take an example for the DFA. So let's take a DFA where our given input is like we have 0 and 1 as an input, and we have to build a DFA that gives us 0 as an output, 0 as an output in the end. So how do we build this as a DFA? So our given inputs are 0 and 1, and first of all we'll build the initial state, which is Q naught. Here we'll taking the input, and it is said that we have to take 0 at the end. So we'll build this 0 Q1. Now Q1, we have to build it in the end state, so Q1 will be our final state. And now we can start with anything. So we have 0 and 1, obviously we'll start with 1 then 0, then we can do anything with that, in the end. But in the end we want 0, so we can take a self loop of 0. We don't need 1, so we'll put a loop back to Q naught, which is our initial state. So this way we can define the DFA of this. And there's two important things in DFA. Here the Q naught is our initial state, and for a given state, like Q naught, we have to define both of our inputs. Like we are given 0 and 1, so Q naught should be defined on both of them. If we make a transition function of Q naught for like 0, so if we give 0 to Q naught, like where it is leading, so it will lead us to Q naught only. And sorry, it will lead us to Q1. And if we take transition function of Q naught to 1, it will lead us to it will lead us back to Q naught. Okay, so here 0 is defined as well as 1 is defined. Same goes for the transition function of Q1. For Q1, if we take 0 and then we find out, then for 0 it is going for Q1 only. You can see it in the diagram, Q1 going for 0, it will be end at Q1. And for Q1 function that goes for 1, it will go to Q naught. So it is defined for both, like 0 and 1. So it is a deterministic finite automata. And this is the DFA for where the given input is 0 and 1, and the ending it is ending with 0. So let's take another one. Another example will be like we'll take the inputs as A and B, where the string must start with A and it should end with B. So let's try this one out. So again, we'll take the initial as Q naught. Now it says start with A. So first of all, we'll take A and then we'll move on to the next state. And it says like we'll end with B. So Q2 will be our final state, starting with A, ending with B. Now, as we are ending with B, let's start here only. from the Q naught. Like we cannot start with B. So what we'll do, we'll take B and put it in a dead state. This QD is a dead state. And we have to define this also like A and B. Like for example, Q naught, it leads that it takes B and it leads us to QD. So what happens after that? If we have to define the states on QD, we have to define the inputs on QD as well. If we take A, then it leads us to QD only. And for B, like you can start with A and doesn't matter how many A's we take, we have to just end with B. So here we'll take B again, and for the A part we'll just lead it back here. So like you can check out any string if you know, if you like A, so A again A, then B. So this one will be checked. The transitions will be same, like like if you build like where does it leads from A, it will lead us to Q1. If we build for B, it will lead us to QD, that is a dead state. You can build QD on as well, and similar transition functions for all of these. So this way you can build a definite finite automata. So this is a DFA. In DFA, the major two things are, like every state should be defined, every input should be defined on that state. Like if we are having two inputs, where does that lead to? You cannot take, and one more thing is important, like like if there is this state, you cannot define this. Like you cannot take same inputs to two different type of sets, different type of states. Like A is going to Q1 and A is going to Q2. This is not allowed in DFA. That is allowed in only in NFA, not in DFA. So let's take one another example, the third one. This will take more understanding. Like let's take an AB as an input, and the number of A's should be one. So defining this, like we will take initial state Q naught. We'll only consider A for now and then move on to B. Like let's go for A, Q1. It will lead. For this, you can also look like epsilon will also be there. So this you go back A and then you define B. Like if A comes, this will not be accepted. Again, it will go back. This will be accepted. A epsilon A A A. Like this time. So one thing I forgot to tell you is that in DFA you have to always start with making a set. Like what will be our output in the end. Like if I say that we are only dependent on even number of ways, so epsilon can be there, A can be there, B can be there, B can be any number. So let's neglect this for this time. A can be there. So you can build a set, then you can easily recognize like what is going on and how we build all of this. Uh, like starting with 0 and ending with 1. So the set will be like 0 1 0 0 0 1 0 1 1 1. So all of these will be contained. So usually try to build a set that will give you more understanding of this. So moving on, we'll continue on with the NFA, like the second part. I'll tell you brief about that. What is NFA? So NFA is non-deterministic automata. It is similar to DFA, but in this, the major two things that I discussed about in DFA, like you cannot have a null transitions, like epsilon, or like your every input should be defined on states. In this, we can do like, like if there are A and B as an input, we can only define A and continue on, or we can take A to multiple states, like Q naught can be delivered to Q1 and Q2. In this, when for the output power transition function, the number of states are also moved. Like the power set of 2 to the power q. In DFA, it was only for q. So continuing with the example, like you can see in this, like q naught leads to q1 and it also leads to q3 for A. So this can do both ways. So that's the power of NFA. Like it's like a bigger subset for the DFA part. Moving on, like it is very easy to construct an NFA rather than converting rather than a DFA. You can also, like, the major part is like you can construct an NFA and then convert it back to a DFA, because every NFA can be converted back to a DFA. So let's take an example. Construct an NFA that accepts the state of all strings over A and B. Here be our input, and each string starts with A. So you can, like, like build with Q naught, A, Q1. That's the final state. And you can just A comma B. Like you don't have to define B for that. Like in NFA, okay, you you cannot start with B, so you have to do like this: B, Q, D, and then A and B. You have to define every state, every input for that. In NFA, this is not required. You can just simply, like, make Q naught. That's the initial state, starts with A, Q1 final state, and the self loop goes A and B. That's done. That's the NFA for you. Very simple NFA. So let's take another one. Like we'll create an NFA where the inputs are same A and B, and it will contain a string. It will tell us the strings which contains A. So moving on, contains A. Let's start Q naught. It contains A. Q1. That's the final state. A and B, whatever can be there. That's the NFA for this. Very easy. So in NFA, the major part is like you can do this. That cannot be done in DFA. You cannot take the same input to two different states, and you don't have to define every input for every state. Like not, if we have an input as A and B, like just define it like this. You don't have to do anything else. B is not there, that doesn't mean. So this is the non-deterministic finite automata for this. We can take another example, like build an NFA where the inputs are A and B, and it ends with AB. So Q naught initial state A, Q1, B, Q2. That's the final state. That's it. You can just leave it there, or you can just build it a little bit more. B starting with A. Here you can end it with A, just like that. That's the NFA for this. So continuing on, let's talk about epsilon NFA. So what is epsilon NFA? So as I told you, in NFA, when we are building an NFA, some states can be in epsilon. Like you don't give any input to the states, and then what the state will perform. So like the same everything. You use a set of states: epsilon input, Q naught initial, F final, lambda is the transaction function. So these transitions are done. For example, you can see as this example as if we give 0 to A, then it leads us to E. If we don't give any input to E, it will lead us to B. Like that's the example of an epsilon closure of the states and all that. Like here's the complete example. So what's the major problem of this? Like if epsilon is given, like there is no input and it leads us to somewhere. So we have to basically convert that epsilon NFA back to the NFA so that we can convert it back to the DFA. So what we'll do? So the first of all, we'll find the closure of each and every state. Like for epsilon for A is will be A, because if we don't give any output to A, then it will stay at A. Let's talk about the big one. Like E. So E will be taking us to B, F, and B will be taking us to D. So it will be B, C, D, E, because if we don't give, it will be staying at A, B. It will also lead us to F and D. So that's all. So here we'll be talking about the conversion of epsilon FA to NFA. So these are the steps that are required to do. Like first of all, taking two vertex having N, will move the vertex V2 having from V1 to V2, and we'll find out all the vertex that start from vertex V2. Then we'll take epsilon of this, all of this closure. We'll also see that if it is a start state, if it is not a start state, we'll make the second vertex as a start state. And we'll check if the next state is final state, then the initial state will also become the final state. Like let's talk bit more than solving the question. Like take this example here. A leads us to 0, epsilon B 1, epsilon C, and 0 and 1. So let's start building this. Like first of all, we'll build the table for this. A, B, C. Oh, I'm sorry. So A, B, C, 0, 1. So if we take A to 0, it will lead us to A only. If we take A as 1, it will lead us to nowhere, which is 5. B for 1 will lead us nowhere. B for 1 will lead us to B, 5, C, C. That's the table. That's the transition function table for this NFA. Now, if we take closure, so the closure of A will be, let's define this as star A. Closure A will be as it goes from A, comma B, comma C. Closure of B will be B, comma C, and closure of C will be C and B. So let's define this. Like if we talk about A and take the epsilon closure A, B, C, and if we talk about the delta function of this, like the lambda transition function. So A leading to 0, B leading to 0, and C leading to 0. A leading to 0 will lead us to A, B leading to 0 will not lead us to anything, C leading to us will lead us to 0. When we find the transition function again, closure, it will be A, B, C, 5, and again C for C. So we'll get ABC and we'll update it here ABC. So this way we'll be removing the epsilon of the NFF. So moving on, like we'll do the same thing for E comma 1, B comma 1, C comma 1. A comma 1 will lead us to nowhere, B comma 1 will lead us to B, C comma 1 will lead us to B, so here will be BC. So we'll update this here also, B comma, let me make it neat, B comma C. So similarly you can find out for B and C as well. So if we take it like B will be B and C, it will lead us to C only. Here we'll write C, and for 1, like it is leading to B as well as C, and it will remain for B and C both. For C it will remain at C and C only. So our end table is like this: A, B, C for 0 and 1, but it will lead us to A, B, C, B, C. Here it will lead us to C, B, C, and C and C. So now if we make the transition table, so now if we make the NFA, now take a look at this. A is a final state, B is a final state, and C is a final state. This is because C was a final state, but if we are not giving any input to B, it will lead to C, which means epsilon. So it will take B as a final state, and similar T goes to A, it will also lead to the final state. So A for 0 can go to B, and A if we give 0, it will go to C. So for 1 it will go to B as well as it will go to C. So B for 0, C, and for 1 also C, and for 1 it will lead us to B, for C it will lead for 0 to 1, and that's the end part, and that's the epsilon for this. Also here it will also lead to here 0. So that's the conversion of epsilon NFP to NFA. So now let's move on and tell you more about Moore and Mealy machine, that are the finite automata with output. So here the major difference is, like, if you give an input, it will give you an output. The majority of the difference lies here. So first of all, let's talk about the Moore machine. So the Moore machine is a finite set automata whose output depends only on the given present state. Keep this in mind, this is very important. It depends only on the present state. In DFA and NFA, there were 5 tuples. Here there are 6. Q is same, epsilon is same, lambda functions are same. Sorry, transition functions are same. Here the delta lies for transition function for output. Q naught is same, and O is the set of finite output symbols that we'll get at the end. So like, this is the finite state automata. So what will it tell us? Like, with output, like, if we are getting 0, then it will lead us to 0 only for x, for the first finite state. And if we give 1, then it will lead us to 1. Like, I'll tell you two things in finite set automata. Like, for example, if we give an n length string input to a Moore machine, then it will return us an n plus 1 length input. Like, let's give this, we can like, give 0 and 1 as an input. So let's give this string 0 0 1 1 0. Okay, so let's find out. So in the start we don't have anything, so it will lead us to x, which gives an output as 0. So now for 0 it will go again to 0, for again 0, then for 1 it leads us to y, which gives an output as 1. Okay, so for y1 it will lead us back to x, which gives an output as 0, and for 0 it will give itself again to 0. So 0 0 0 1 0 0. So the input string was of 5 length and the output string is of 6 length. So this is the majority difference. In the Mealy machine is similar to Moore machine, but here the major difference lies, like, in the Moore machine there was only the present state which was important, like what is the output, it only depends on the present state. In this, the input also depends, like what is the present input and what is the present state. These two things are majorly important. So similarly, 6 tuples, all of the same things. This is the Mealy machine. Like, for Q1 state, if we get an 0, it will give 0 as an output. If we get 1, and it will give 0 as an output, and it will lead us to Q2. So this is the Mealy machine for this. Like, for example, in Mealy machine, if we give an n length string, and it will give you also the n length output only. Like, if we give this string 0 0 1 0, so 0 leads us to 0, 0 again it leads us to 0 at Q1 only, and if we get 1, it will give an output 0 and it will lead us to Q2. In Q2, if we give 0, it will lead us to Q2 and it will give an output of 1. 0 0 1 is the output, and the string length is the same. So let's try out a question. Construct a Moore machine that makes a set of, like, A and B is an input, and it waits 1 as an output for every occurrence of EB. Like, that's the majority difference and major importance of Moore machine. Like, if we give an input EB as a substring, it will give us 1 as an output. So let's start out. Q naught initial state. 1 minute. Let's build this again. And because we have to give some space here. A, Q, B, Q2. This is the final state, and AB it counts, it gives us as 1. We can start with anything B 0 0. 0 is just like an output, like for anything other than AB as a substring, it will return 0. So AB, now we can put A again, A, it will be accepted, but it will give 0 as an output, so we don't have any problem. If we get AB, it will give us 1 as an output, that is important. Here we loop A back again. We cannot put self loop here because A, B, B, okay? A, B, 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 that will continue on, but we can accept that. So, like we'll do this A, B, B, B. So we put a subset here. A, B, B, B. Like we can check a string A, B, 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 B. It will give us one as an output. Like if we take a loop back, then it will not return us A, B, B, 0, 1, A, B, again 1. So that will prove as an output. So let's take another example of a Moore machine. Like let's try out a simple one, which is like 0 and 1 will be given as an input, and we have to find out that the number of ones is even or odd, and based on that we'll write if the number of ones are even, the output will be 1, and if not, 0 will be the output. So going on, initial state, we'll take 1 to 1, a similar DFA kind of thing. 1 here we put 0, here we put 1, and for 0 we'll make it like this. So that's the Moore machine, very simple. And if you want to convert it into a Mealy machine, that's also pretty simple. Like take the initial state 0 leading to 1, 1 leading to 0, q1, 0 leading to 0, 1 leading to 1. That's the easy part. That's the straightforward conversion of Moore to Mealy. And when you are converting these Moore to Mealy, always remember that if Moore machine has n states, then the Mealy machine will also have n states. But the reversal is not true. If Mealy machine has m states and Moore machine has n states, so the number of states can be m cross n. Okay, so that's the major difference. Uh, like let's try another one, Mealy. That takes a like string input, and for every occurrence of one sorry AB, it will give us one as an output. So let's start this. Q0 initial state A, Q1, B, Q2. So for AB we'll get 1, another 0, B 0 here, A also 0, A 0, and revert this back to 0. So that's here, like every time it count is AB, it gives 1, similar to the Moore machine. So that's all from my side for the finite automata. These are the major things that you can remember from this video. DFA, NFA, in this there are 5 tuples majorly, and the major part is like initial state, final states. You cannot take, like if you're given 2 inputs, each input is defined and all states are defined. NFA can be like anything you want, like these two things doesn't matter in this. Epsilon NFA, you have to majorly convert it back to the NFA. And for the output parts, there are two: Mealy machine, Moore machine. Moore machine depends only on the present state. Mealy machine depends on the present state and input. So that's the major part of this video. Thank you.